I'll be talking about observations of anomalous and galactic cosmic rays during the last several solar minima, in fact. And I'll be limiting the topic to the observations. I'll leave the interpretations and the meaning of this all to the theorists and modelers and people with more expertise in this field, or at least people that have lived through more solar minima than I actually have. Just to be sure everybody's all on the same page, this is the record of galactic cosmic rays at 1 AU as measured by a neutron monitor, in this case the Newark neutron monitor, for the last several solar cycles. And during the apositive solar minima, which is when the magnetic field at the north pole of the sun is coming outwards, the time profiles of the GCRs tend to be flat and broad and last for quite a while, whereas when the polarity is reversed at A negative, like we're in now, you tend to get a very spiky sort of thing like this. For comparison, shown on the right axis here and plotted upside down just to confuse you, is the sunspot number during the same time. And what you see is that typically, it's most easier seen at these A negative minima, typically the sunspot minimum leads the modulation minima or the GCR maxima by about a year or so. And so if the experts are right and sunspot minimum really occurred in December 2008, and I think the jury's probably still out on that, then we ought to be entering modulation minimum right about now. Now, I'm showing the Newark neutron monitor here just because that happened to be the one I used, but of course there's many other neutron monitors to choose from. Not as many as there used to be, unfortunately, but still quite a few. And if you compare them, here's just a sample of some of them scaled as power laws and laid on top of each other. Some of them actually go back further in time than Newark does, and you see the last part of this A negative cycle here and part of the A positive. When scaled in this manner, they actually all agree with each other fairly well during this last A negative, but if you look carefully, you see that by the time you get to the present here and even up into this last solar minimum, there starts to be some divergence. For the purposes of this talk, I'm not going to worry about that too much. I'll let that to the neutron monitor experts to discuss and worry about and argue about. The main point is that I think everybody agrees that at the present time here, at the very end of this run, we are at the highest GCR intensity, certainly for this solar minimum, and in many cases, and for most of these observers at least, the highest we've seen in about 50 years or so. Another way of looking at this is if you consider the solar modulation parameter phi. This is from work of Usoskin et al., who uses a network of neutron monitors, including many that I haven't actually shown you and not including Newark. And they, too, find that at present the modulation level for galactic cosmic rays is the lowest seen in 50 years. So we're definitely at a very deep solar minimum. Another indicator, not so much of the severity of the solar minimum, but at least of its timing, is shown here by the co-rotating interaction region particles. In his Parker lecture, Len Berlage described CIRs. High-speed solar wind streams, such as these ones here, overtake and interact with slower speed streams, and shocks form, particles get accelerated. These here are about 2 to 6 MeV protons measured by stereo over the last several years. And you see, even during this, what's otherwise a quiet period, I mean, we haven't seen a big SEP event in 3 years now, otherwise quiet period, we've had regularly occurring increases in energetic particles due to co-rotating interaction regions until about this year. And now even those have pretty much died down. The intensities are much lower, the frequency is much lower. Not surprisingly, at the same time, the drivers of these CIRs, the high-speed streams, have become mediocre speed streams at best. They're just struggling to reach 500 kilometers per second. So the sun has definitely gotten quiet in terms of particles. Solar wind is quieted down, CIRs are quieted down, GCRs are way up. What about the anomalous cosmic rays, ACRs? Well, these are data here from the ACE mission, which was launched at the tail end of the last solar minimum. These are anomalous cosmic rays, relatively low energy oxygen here from the CIS instrument, and you see that at present, this is where our intensities are at. This is where they were at the end of the last solar minimum. ACR intensities have not yet recovered at 1 AU to where they were at the end of the last solar minimum. GCRs, on the other hand, in this case several hundred MeV per nucleon iron from another instrument on ACE, again, are elevated from where they were. And in both these panels, I compare with the neutron monitor values by scaling as a power law. And yes, I am using Newark, and it agrees pretty well here with the CRIS data, the GCRs here. If you want to pick one of these other neutron monitors that come out a little bit lower, great. You'll probably get better agreement here, but you cannot make it agree here. When it's tracked such that it agrees nicely here at the last solar minimum, there's a big discrepancy at this one, and it starts somewhere down around here, near the last solar maximum, about the time of the polarity reversal. Now, there are other ACR species too. In the interest of fairness, I should show you them rather than just show you different neutron monitors, but not the ACRs. Here's helium, nitrogen, and helium, nitrogen, and neon. And here they are all overlaid on each other with oxygen. I've not subtracted the GCR background, so they all kind of bottom out at different levels here. But you see that they all track each other pretty well. And in fact, the main point is none of them have recovered to what their levels were at the last solar minimum. So is that usual or unusual? Actually, one of the earlier speakers mentioned that some of these things we don't have a long record for. Well, we have the extra handicap in that since it's a significant difference between the two polarity cycles, we have effectively half the number of records that some other people do. But it seems to be usual. This is the ACR intensity, again, the ACE data that I showed you, and extending back in time using SAMPEX and some earlier missions like the IMPS and OGOs, and the neutron monitor scaled on top of it. And you see that the same scaling that I used between the two that works well here worked fine during the last A positive cycle. This isn't working in this A negative cycle, and apparently didn't work in the last one either. A sparser number of ACR data points, but seems to be falling short there too. What we find at 1AU is that at A negative cycles, the GCRs have a higher peak intensity than at A positive cycles. In the outer heliosphere, that's true for the ACRs as well. The ACRs are factors of several higher at A negative cycles than at A positive. At 1AU, that doesn't seem to be the case. Certainly it's not true here, unless we haven't quite gotten up there yet. But in this case, too, it looks like ACRs are actually lower in peak intensity at A negative cycles at 1AU than at A positive. So if I can't scale it like this, how are these two related here, the ACRs and GCRs? Well, if I just simply plot one versus the other, this is the ACRs here, GCRs here, log-log scale, you see it's basically aligned. That's where I get the power law index of 30 that I showed in the other plot from the decline from 1997 down to solar max. It's bounced around down here for a while, and it's coming back up along essentially the same slope line. The index has not changed. The offset has. So all the differences in modulation between the positive and negative cycles, whatever they boil down to at 1AU, basically boils down to a change in the scale factor between the two in some fashion. How does this compare to the longer-term historical record? Well, you can take a look, although again the data is a little sparser. This is the plot you saw before. If I split the data at the maxima and plot effectively the same sort of hysteresis loops, if you will, this is the one we just saw. We start here, come down, come back up. The last positive to negative transition here looks something like this. I didn't put the error bars on. This obviously bounced around a lot, but it looks pretty similar. Same direction of change, basically the same slope. The one in between the negative and positive, the direction is reversed. And if you put all this together and changing the directions with the different polarities and taking into account the fact that you peak at different values with the ACRs peaking at positive and rather than negative and the GCRs going the other way, you basically get at least what in a cartoon fashion looks topologically like a figure 8. You go around the loop at the positive cycle in one direction, negative in the other, and you connect together like that. So if I were to predict what's going to happen when this starts coming down, if it starts coming down, it's not going to close the loop. It's not going to retrace its step. It's going to kind of split the difference between the two and come down like that. Am I right? Check back in a couple of years. So most of what I've been showing you has been all types of particles at one particular energy. Is some of this an energy-dependent effect? The GCRs that I've been showing you are up at GeV energies or hundreds of MeV energies. The ACRs are down at a couple tens of MeV. Is it energy-dependent? I would say no. Here are spectra for 6 different species from ACE, 3 of which have a large ACR component, oxygen, nitrogen, and neon, 3 which don't, carbon, silicon, and iron. And I'm showing you 2 spectra in each case, one in lighter colors taken from the beginning of the ACE mission, the tail end of the last solar min, and one using recent data up to about a month ago or so, shown in the darker color. And you see the ACRs themselves, the new stuff, the dark stuff, hasn't quite gotten up to where it was before for either oxygen or nitrogen or neon. But by the time you get to the higher end of the spectrum where the GCRs dominate, they're all higher. And that's true even for these GCR species that don't have an ACR component. That is, if you go down to 20 or 30 MeV per nuke carbon, not only have those GCRs recovered, they are actually elevated compared to where they were last time. So here's these on the bottom is the ratio of the old stuff, of the new stuff to the old stuff. You see a constant, well, essentially constant across the board, 20% or so enhancement for all these species for the GCRs. It gets a little noisy down here, but if you follow the carbon line, it's not inconsistent with it. And while at the same time the ACRs are down at 85, 90% or so of the level they were at the last solar min. So what's causing all this? Well, in some of the earlier talks this week, we heard various things. In fact, in some of the earlier talks this session, we heard about the changes in the B field at the sun, and some of the other talks emphasize the changes in the B field in interplanetary space. That undoubtedly plays a role. There are, of course, differences in the dynamics pressure of the solar wind and the speed. There aren't a whole lot of CMEs going on these days anymore. I can't discuss all these things in the time available, but I will mention changes in the tilt of the heliospheric current sheet, partly because a lot of the work was done by our distinguished co-chair here. Jacobi and Thomas back in '81 pointed out that during A negative cycles, the drift direction of charged particles, positively charged particles, into the inner heliosphere is along the heliospheric current sheet. It's reversed during A negative cycles. They come in from the poles, go out along the current sheet. And so the ease of access to the inner heliosphere depends on the tilt angle. The larger the tilt angle, the bigger the amplitude of this wiggle that gets generated, the longer the path length, the more difficult it is for particles to get in. What's the tilt angle been doing lately? Well, this is data from the Wilcox Solar Observatory. Other people have shown the magnetic field measurements from Wilcox. This is my rendition of that. But this is the tilt angle from the Wilcox Solar Observatory over the last few cycles. Again, it only goes back 3 cycles, but we'll take what we can get. In all previous cases, the rise has been fairly rapid, and it's decayed back down to low tilt angles, you know, on this kind of time scale. Here, I've got dashed lines on there just done by eye. This is what it's doing now. It's coming down a lot more slowly. That's a lot more dramatic if you actually lay these on top of each other, like this. Cycle 21 in blue, 22 in red, and the most recent cycle in black. They all rose to peak tilt angle with basically the exact same rate. And the last 2 cycles came down more or less the same. Lots of fluctuations, but they sort of started at the same point, ended at the same point, and took about as long to get there. This present cycle started coming down about the same rate and then decided to really slow itself down. And it's a little sobering to realize that by this point in time, in the last 2 solar cycles, this late in time since the onset of the tilt angle increase, we were well into solar max, and now we're just barely getting into solar min. So the sun is running way behind schedule, hopefully not like this session might be. So, given that the high tilt angle tends to block the ACRs from coming in, and given that it's been high until recently, does that explain why you get relatively low ACR intensities? Sounds plausible, but never one to leave well enough alone. Decided to take a look and check it out. There's a lot of stuff on this plot, but you've seen some of it before. The red data is the ACR intensities on this scale. The blue data is the scaled neutron monitor overlaid on top of it, just as you've seen before. And now I've added the tilt angle in a thick black line, plotted again upside down here on this axis. Now, if you look at this last A negative here, the black line from the tilt angle and the blue from the neutron monitor are in great agreement with each other, almost wiggle for wiggle. It's not surprising. That's what they're supposed to be doing. The agreement actually even lasts well into this A positive cycle here. And it really starts deviating about the time you come out of the A positive minimum and go into the next maximum. And that makes sense because at that point in time, the particles are coming in from the polar regions. They don't much care what's going on down in the ecliptic at the low latitudes. The current sheet comes up relatively rapidly. The particles only reluctantly sort of drop off. And they did much the same sort of thing at the tail end of the last A positive cycle that we had. Okay, so that's the last A negative cycle. Here's what we have now. Nothing is agreeing with anything else anymore. The way it's been plotted here, the blue neutron monitor and the tilt angle are lying on top of each other. So if we look at the given tilt angle now, the GCRs are well above where they were for that same tilt angle during the last A negative. The ACRs are plotted here at about the same level or maybe a little bit below. Here, again, for the same tilt angle, the ACRs are actually high. In an absolute sense, the ACRs are about normal, maybe even a little on the low side. But for a given tilt angle, which is supposed to dominate the ACR transport, they're actually high this time around too. So something has changed in the scaling between the neutron monitor, the tilt angle, and the ACRs in this cycle. And this change occurred back here. Yeah, it's a really quiet solar min. Yeah, the solar wind is down. There's not much going on, anything like that. This change in the scaling started back here around solar max, about the time that the polarity reversed. So I don't know what it is, but I would like an explanation for this from the modelers, the theorists, and anybody who's able to provide one. So to summarize, the ACR intensities are about where they should be compared to the last solar minima. But they certainly took a good long time to get there. GCRs are effectively at record highs for the space age, at least, although as we heard in other talks, they've probably been a whole lot higher in the distant past. The scaling between the ACRs and neutron monitors is different from it was in the last solar minimum, the A positive solar minimum, but it seems like that's typical. That doesn't seem necessarily to be unusual. It's not due to an energy-dependent effect, at least in the sense that the low-energy GCRs are elevated from where they were. ACRs are depleted. something definitely changed between the scaling, between the tilt angle and the particle intensity since the last cycle. Both ACR and GCR intensities are high for a given tilt angle compared to where they were last time. These changes in the interplanetary conditions, the B field, the solar wind speed, etc., certainly have to have something to do with this. It's very easy to see that all these things go in the direction such that it's going to be easier for particles to get in. So the GCR transport should be much easier. That probably explains why you get the GCRs higher. It's not so trivial to figure out what it does for the ACR since they're effectively local. They're accelerated presumably at the termination shock or in the heliopause or somewhere nearby. That's all thrown into a hat too because of the whole new IBEX measurements and the Voyager measurements in terms of figuring out exactly how and where the ACRs are coming from. But they're local. If you change the interplanetary parameters, what does that do to the source of the ACRs? What does it do to their acceleration efficiencies, the size of the region, the source intensity? Does it go up? Does it go down? By how much? I think working that out will probably give the answer to why these things are tracking the way they are, but I think that's still work that needs to be done, and that's where the challenge still lies. I'm going to echo our first speaker and say I'm not going to try to predict what's going to happen, given what we're seeing now. It's going to be interesting to watch and find out what's going to happen, and probably if you check back in a couple of years, we'll at least have some better idea what's going on then. Thanks very much. To the theorists and modelers and people with more expertise in this field, or at least people that have lived through more solar minima than I actually have. Just to be sure everybody's all on the same page, this is the record of galactic cosmic rays at 1 AU as measured by a neutron monitor, in this case the Newark neutron monitor, for the last several solar cycles. And during the apositive solar minima, which is when the magnetic field at the north pole of the sun is coming outwards, the time profiles of the GCR sunspot minimum really occurred in December 2008, and I think the jury's probably still out on that. Then we ought to be entering modulation minimum right about now. Now, I'm showing the Newark neutron monitor here just because that happened to be the one I used, but of course there's many other neutron monitors to choose from. Not as many as there used to be, unfortunately, but still quite a few. And if you compare them, here's just a sample of some of them scaled as power laws and laid on top of each other. Some of them actually go back further in time than Newark does, and you see the last part of this A negative cycle here, and part of the A positive. Tend to be flat and broad and last for quite a while, whereas when the polarity is reversed at A negative, like we're in now, you tend to get a very spiky sort of thing like this. For comparison, shown on the right axis here and plotted upside down just to confuse you, is the sunspot number during the same time. And what you see is that typically, it's most easier seen at these A negative minima, typically the sunspot minimum leads the modulation minima or the GCR maxima by about a year or so. And so if the experts are right and positive, when scaled in this manner, they actually all agree with each other fairly well during this last A negative. But if you look carefully, you see that by the time you get to the present here and even up into this last solar minimum, there starts to be some divergence. For the purposes of this talk, I'm not going to worry about that too much. I'll let that to the neutron monitor experts to discuss and worry about and argue about. The main point is that I think everybody agrees that at the present time here, at the very end of this run, we are at the highest GCR intensity, certainly for this. I'll be talking about observations of anomalous and galactic cosmic rays during the last several solar minima, in fact. And I'll be limiting the topic to the observations. I'll leave the interpretations and the meaning of this all to